Hello everyone, welcome to Introduction to Data Mining class. In this unit, we will introduce histogram, scatter plot and correlation, and proximity matrix. Histogram, as shown on the screen, is a graphical display of tabulated frequencies, shown as bars. Plotting histograms is a graphical method for summarizing the distribution of a given attribute. If the attribute is nominal, such as automobile model or item type, then a vertical bar is drawn for each known value of x. The height of the bar indicates the frequency, that is, the count of that attribute value. The resulting graphic is more commonly known as a bar chart. If the attribute is numerical, the term histogram is preferred. The range of values for the attribute is partitioned into disjoint consecutive subranges. The subranges, referred to as buckets or bins, are disjoint subsets of the data distribution for the attribute. The range of a bucket is known as the width or bin width. Typically, the buckets are of equal width. For each subrange, a bar is drawn with a height that represents the total count of items observed within the subrange. For example, based on the pixel intensity of a grade level image, an image histogram can be built to describe the distribution of pixel intensity. You can see such image histogram on your digital camera to tell you whether a photo is underexposed, as shown on the left, or well exposed, as demonstrated in the middle, or overexposed, as depicted on the right. An underexposed photo will look darker so that you can observe the bars in the image histogram shift to the left. Contrarily, an overexposed photo will look brighter so that you can observe the bars in the image histogram shift to the right. A scatter plot is one of the most effective graphical methods for determining if there appears to be a relationship, pattern, or trend between two numeric attributes. It provides a first look at bivariate data to see clusters of points or outliers, etc. To construct a scatter plot, each pair of values is treated as a pair of coordinates and plotted as points in the plane. As shown on the right, this scatter plot example explores the possibility of correlation relationships between two attributes, unit price, and items sold. Two attributes are correlated if one attribute implies the other. Correlations can be positive, negative, or null, which means uncorrelated. The scatter plot on the left demonstrates two positively correlated attributes. As you can see, when one attribute increases, the other attribute also increases. The scatter plot in the middle depicts two negatively correlated attributes. As you can observe, when the attribute in the x-axis increases, the other attribute in the y-axis decreases. The scatter plot on the right illustrates two uncorrelated attributes. The points are randomly scattered in the plot, which indicates that the two attributes are uncorrelated. In data mining applications such as clustering, outlier analysis, and nearest neighbor classification, we need ways to access how alike or unalike objects are in comparison to one another. For example, a store may want to search for a cluster of customer objects, resulting in groups of customers with similar characteristics. For example, similar income or similar area of residence and age. Such information can then be used for marketing. A cluster is a collection of data objects, such that the objects within a cluster are similar to one another and dissimilar to the objects in other clusters. Outlier analysis also employs clustering-based techniques to identify potential outliers as objects that are highly dissimilar to others. Similarity and dissimilarity measures, which are referred to as measures of proximity. A similarity measure for two objects will typically return the value 0 if the objects are unalike. The higher the similarity value, the greater the similarity between objects. Typically, a value of 1 indicates complete similarity. That is, the objects are identical. A dissimilarity measure, such as distance, works the opposite way. It returns a value of 0 if the objects are the same, and therefore far from being dissimilar. The higher the dissimilarity value, the more dissimilar the two objects are. The upper limit for dissimilarity may vary due to the fact that the distance between two objects may be infinite. Data matrix and distance matrix, or similarity matrix, are two commonly used data structures for storing data objects and store the dissimilarity values or similarity values for pairs of data objects. Data matrix stores each data object as a row in the matrix where Each column represents an attribute. All data objects in the matrix should have the same set of attributes. The matrix on the right demonstrates a data matrix with n data points. As you can see, the subscript on the left in each column starts from 1 to n, which indicates there are n objects in the matrix. The number of attributes for each data object is p. As you can see, the subscript on the right in each row starts from 1 to p, which indicates there are p attributes for each data object. Distance matrix or similarity matrix stores the dissimilarity values or similarity values between each pair of data objects in the data matrix. And thus, distance matrix or similarity matrix are a square matrix where the number of row and number of column equals to the number of data objects in the data matrix. Specifically, if we have n data objects in the data matrix, then the distance matrix or similarity matrix should be a matrix of size n by n. The n by n matrix enables us to store the proximity measure between pairs of data objects. For example, the matrix on the right shows the concept of distance matrix, where the first row indicates the first data object and the last row indicates the last data object in the data matrix. Similarly, the first column indicates the first data object and the last column indicates the last data object in the data matrix as well. This matrix allows us to measure proximity between two objects in the data matrix by selecting an object from the row and selecting the second object from the column. The proximity measure of the two selected objects will be stored in the cell at the intersection of the selected row and column. As you can observe from the distance matrix demonstrated on the screen, the diagonal cells are all zeros. Because this dissimilarity measure indicates the distance between the same data object, which should be 0. In addition, all values stored in the lower triangle part of the matrix should reflect the values stored in the corresponding upper triangle part of the matrix. For example, the value stored in row 2, column 1 should be identical to the value in row 1, column 2. Because we measure the distance between the two objects, swapping the two objects should obtain the same distance. Therefore, we typically only need to fill either the lower triangle part of the distance matrix or the upper triangle part of the distance matrix to omit the redundant data storage. Any questions?